Quantum confinement can be understood by imagining a small space like a tiny box that traps particles such as electrons. When particles are confined to this small space, their behavior changes dramatically, much like how your movement would be restricted in a cramped room. In the quantum world, this confinement causes particles to exhibit new properties due to the limited space, which forces them to take on specific energy levels. An analogy is like playing a musical instrument. If you shorten the length of a guitar string, the pitch of the sound gets higher. Similarly, when particles are confined in smaller spaces, the energy of the particles increases. This effect is often seen in nanomaterials, such as quantum dots, where changing the size of the particle alters its color or electrical properties because the electrons are squeezed into smaller spaces. Quantum confinement in nanotechnology can be seen in various practical applications. One notable example is quantum dots, which are used in LED displays and TVs. These tiny semiconductor particles, when confined to a nanoscale size, emit different colors of light depending on their size. Smaller quantum dots emit blue light, while larger ones emit red light. This size-dependent behavior is due to quantum confinement, which affects the energy levels of the electrons inside the dots. The equation that describes quantum confinement typically involves the Schrödinger equation for a particle confined in a potential well, such as in a particle-in-a-box model. The energy levels of a confined particle, like an electron, can be described by E sub n equals n squared times h squared divided by 8ml squared, where E sub n is the energy of the confined particle in the nth state. N is a quantum number, which is an integer that indicates the energy level. H is Planck's constant. M is the mass of the particle, for example, an electron. L is the length of the confinement region, such as the size of the nanoparticle. This equation shows that the energy levels depend inversely on the square of the confinement size, L. This means that as the particle's confinement gets smaller, like in nanoparticles, the energy spacing between levels increases. This change in energy levels gives rise to observable effects of quantum confinement, such as color shifts in quantum dots or changes in electrical properties. In this example, we'll estimate the minimum diameter of a quantum dot that can effectively confine an electron in copper, such that the ground state energy is equal to the Fermi energy, which is 7 electron volts, or approximately 1.15 times 10 to the negative 18 joules. There is more than one way to approach this calculation, so let's look at two strategies. Strategy 1. The wavelength of an electron, called lambda, is Planck's constant, h, divided by the electron's momentum. P, this momentum is equal to the electron's mass, m, multiplied by its velocity, v. For copper, free electrons at the Fermi level move at a speed of approximately 1.50 times 10 to the power of 6 meters per second. The mass of an electron is approximately 9.11 times 10 to the negative 31 kilograms. So, substituting these values, the wavelength lambda equals Planck's constant, or 6.626 times 10 to the negative 34 joule seconds, divided by the product of the electron's mass and velocity, which gives approximately 4.86 times 10 to the negative 10 meters. This results in a wavelength of 486 picometers. Thus, the characteristic dimension, d, which is the diameter of the quantum dot, must be at least d equals lambda divided by 2, which is 486 picometers divided by 2, giving us approximately 243 picometers. Strategy 2. Now let's try the potential well model. This model suggests that the energy of an electron, E, is proportional to Planck's constant squared, divided by 8 times the electron's mass, multiplied by the quantum dot's diameter squared. To solve for the diameter, we rearrange the equation to d equals the square root of Planck's constant squared, divided by 8 times the electron's mass, multiplied by the electron's energy. Substituting the values for the ground state energy of the electron, which is 7 electron volts, or 1.15 times 10 to the negative 18 joules, We get d equals the square root of Planck's constant squared, or 6.626 times 10 to the negative 34 joule-seconds squared, divided by 8 times the electron's mass, or 9.11 times 10 to the negative 31 kilograms, multiplied by the energy, or 1.15 times 10 to the negative 18 joules. This results in approximately 2.45 times 10 to the negative 10 meters.